Okay, so this is going to be a review video for lecture 10 on energetics, and we'll start off by talking about metabolism. And we can define metabolism as the sum of all chemical reactions that an organism needs to survive. And the two main types of metabolism are catabolic metabolism and anabolic metabolism. So first, catabolic metabolism means that we're breaking down bigger, more complex molecules into smaller ones. And so in the lecture, we talked about how we can break down macromolecules into their subunits. So an example for this would be breaking down a protein into its corresponding amino acid. And so for anabolic, it's the exact opposite, where we're building up bigger complex molecules from smaller ones. So just the reverse of this reaction right here. So going from amino acid to protein. All right, so, and to give you guys another example, we can look at this diagram to the left here. So we can start here at the top with glucose. And in this reaction pathway, glucose goes all the way down until it becomes 2-pyruvate. So the reaction going from glucose to pyruvate is actually a catabolic reaction because it's breaking down glucose, which is a bigger molecule, into pyruvate, which is a smaller molecule. And if we were to do the reverse reaction, so we go from pyruvate to glucose, we are building up a bigger complex molecule from a smaller one. So we're going from smaller pyruvate to a bigger glucose molecule. And if we notice here that for the catabolic pathway, going from glucose down to pyruvate, we can see that ATP, net ATP of 4, is released. So from that, we can conclude that catabolic pathways release ATP. And so now when we look at the anabolic pathway going from pyruvate back to glucose, we notice that it actually requires ATP. So 2 ATP here, 2 GTP, which is just an ATP equivalent, and another 2 ATP here. So anabolic requires ATP. Just as if we're going from a protein down to an amino acid, it would release ATP. And if we're going from an amino acid to a protein, it would require ATP. So to determine whether a chemical reaction requires or releases energy, we have to talk about Gibbs free energy, which is the amount of energy in a system that is able to do work. And Gibbs free energy will tell us whether a reaction is spontaneous or non-spontaneous. So spontaneous reactions will not require energy to proceed. Non-spontaneous reactions will require energy to proceed. So to determine whether something is spontaneous or not spontaneous, we have to look at the sign of delta G. So if delta G is a negative value, then that would mean it is spontaneous. And if delta G is positive, then it is non-spontaneous. So the delta G is basically the final free energy minus the initial free energy. And if your final energy is a lot higher than your initial free energy, then your reaction would be non-spontaneous. And if your final energy is smaller than your initial energy, then that would mean your reaction would be spontaneous. And delta G depends on entropy, which is delta S, enthalpy, which is delta H, and temperature measured in Kelvin. So entropy is just a disorder in the system. So this example here shows that a cube that's cut into 4 is basically breaking down into 4 little squares in a line. And that just represents how there is more disorder or more entropy in the system. And so for delta H is enthalpy, which is the total energy of the system. And it's defined as delta G plus temperature times delta S. And so all these will determine whether a reaction proceeds spontaneously or non-spontaneously. And if we look at this above example where I talked about how catabolic pathways release ATP and anabolic pathways require ATP, we can say that catabolic pathways are spontaneous because they do not require energy. Instead, they release energy. And then the opposite for anabolic. So anabolic would be non-spontaneous. And we can do this using the equation as well. So, alright, so for catabolic pathways, we can use delta G equals delta H minus T delta S to determine if it's spontaneous or not. Same for anabolic pathways, but we'll just do catabolic here, and then anabolic pathways, you probably figure that out. So for catabolic pathways, our delta H is actually going to be negative. So delta H is the chemical energy in the bonds. So when we're going from a bigger, more complex molecule to a smaller one, our energy in the bonds will decrease. So it's going to be a negative value. And then temperature is just T. And then for delta S, which is entropy, if we're breaking down something from bigger to smaller molecules, we are creating more disorder in the system. So our delta S value would be positive. So it would just stay delta S. And then since we have two negatives here, this is going to give us an overall negative delta G value, meaning that catabolic pathway is spontaneous. So we'll look at the free energy diagrams for both non-spontaneous and spontaneous reactions. So starting off with non-spontaneous, we said that the delta G value for a non-spontaneous reaction is positive. So having said this, we know that delta G equals G final minus G initial. So in order for delta G to be a positive value, our final free energy, which means free energy in our product, should be much higher than the free energy in our initial, which is the reactants. So if we were to draw a free energy diagram for non-spontaneous reaction, we would basically want our products to have much higher free energy. So if we start down here and go up like so, and this would label as our products, and this as our reactants. You can see that the y-axis gives us free energy, so the products will have a much higher free energy than the reactants, thus giving it the positive delta G value. And now, so for the spontaneous reaction, it's the opposite. So our reactants will have a higher, our reactants are right here and our products down here. Our reactants will have a higher free energy value, and our products will have a smaller free energy value, and that gives us a delta G, which is negative. So this was a clicker question that was in lecture today, and it asked which of the following arrows shows a delta G for both reactions. So to determine this, we can write down what our delta G equation is. So G final minus G initial. G final is our product and G initial is our reactants. And if we label our products and reactants for both the blue reaction, so reactants up here for the blue, products down here, and then for the black, reactants up here and products going to be down here. Basically, the only difference that these two reactions have is the hump right here. So this and this hump is basically just the activation energy, which means that the energy required to kind of go over the transition state for the reaction, and the activation energy, the reaction with a lower activation energy will proceed faster. But our delta G equation doesn't have activation energy. It doesn't take into account any activation energy. And if we notice that the products free energy for both the reaction is the same, and the reactants free energy for both the reactions is the same, then our answer would have to be A right here. Because for both reactions, the products are going to be down here, and for both reactions, the reactants are going to be up here. So that would be the answer for that. So how do anabolic reactions proceed if they don't occur spontaneously? And the answer for this is energetic coupling. It's basically when a exergonic reaction is coupled with an endergonic reaction, so that the endergonic reaction will proceed. And the conditions for this is the net delta G has to be negative for it to be a spontaneous reaction, and the reactions have to occur together. So if we look at example A here, ATP, the hydrolysis of ATP to ADP and phosphate gives you a delta G that is negative. And glucose, the reaction of glucose and phosphate to glucose 6-phosphate and water is a positive. And so to drive that reaction, these two reactions couple together, and the difference between their delta G's will give you the coupled reaction. All right, so for B, it's the same idea here. This has a negative delta G, exergonic or spontaneous reaction, coupled with the other ADP plus phosphate to ATP, which has positive delta G, and the resulting delta G is a negative value. So lastly, we'll talk about enzymes. And in biology, enzymes are what are known as catalysts. And catalyst is something that speeds up a reaction. So if we look at this free energy diagram, we notice that there is the black solid line represents one reaction, and the blue dotted line represents another. And if we were to ask the question, which reaction proceeds faster, answer would be the blue reaction. And so why is that? It's basically because of this right here. For that, the blue one, and this for the black one. So these humps represent a transition state, and the energy that is required to overcome a transition state and go into the product is known as activation energy. Energy. So what enzymes do, their role is to lower the activation energy. And if you lower the activation energy, the reaction will proceed faster. And just like the example provided here, the clicker question, the activation energy does not change the delta G of the reaction, like the total delta G of the reaction, because delta G, like we mentioned before, is dependent on just the final free energy and the final or the initial free energy. So whether a reaction is faster than the other reaction, that does not mean that the faster reaction will have a greater delta G.